It's a great pleasure to Andy Sederman talking to us. He's from the Department of Chemical Engineering in Cambridge, and I think he's interested in very fast MRI imaging. Thank you
very much. Thank you for giving me the invitation to talk here as well. So as was just mentioned, although this is essentially or mainly a biomedical focused conference, I'm from the Department of Chemical Engineering and Biotechnology. And indeed, I'm going to be talking really only about the application of magnetic resonance imaging to engineering type systems. But of course, it's really about the capabilities and the advances and the progress in terms of the acquisition techniques and the speed, which of course are applicable to preclinical, clinical type systems as well. So I shall also specifically be focusing on dynamic processes, say speeding up image times so that we can do fast look at transient systems. I'll start off with acknowledgements in case I forget at the end. So I've got in red circles there the other main academic staff in the group. It's obviously a collaborative effort. There's Lynn Gladden here and Mick Mantle, who currently work in the group. And then also at the end there's Dan Holland, who has since moved to New Zealand for a position there. And the work I'm talking about today is predominantly done by, or large parts of it anyway, by Alex Taylor, and just hiding it about there, Martin Benning, who's actually now working here in DAMPT with Corolla. And I should say funding bodies as well. We have a number of different companies, but this in particular was EPSRC and Microsoft Research Cambridge. So an outline of the talk, I'm going to start off by, well, in fact I'm going to start off by saying a few words about chemical engineering and what that is and why we might want to use MRI in chemical engineering, and have a brief introduction to some of the capabilities, the basic ideas behind magnetic resonance imaging. And then I'm going to look at ways in which we've been speeding up velocity imaging in particular with different MRI techniques, so that we can look at dynamic flows. And these may be systems in which we've just got the flow which is changing with time, or for example in turbulent flows for single phase liquid, or in cases where the geometry is changing as well with two-phase flows. And I'll touch on the ideas of undersampling, compressed sensing as well. And then finally just think about, are there other ways that we can get useful information if we think about acquiring fewer data points as we are with compressed sensing. Maybe we can go further and actually reduce data points needed even further. Hopefully. Right, so what is chemical engineering? Really it's the application of physical and life sciences to understand and develop products and processes. The sort of things that we're looking at predominantly are, I would say, engineering and physical sciences, applications of magnetic resonance, and the areas in particular that we're concentrating on, focusing in, are the oil industry, chemical process technologies such as catalysis and chemical transformations, and the pharmaceutical industry in particular, controlled release dissolution type systems, and probably materials processing, soft solids should go in there as well. But we're often looking at things which have got different chemical species and maybe chemical reactions. Often as chemical engineers we're looking at mass transport, so fluid flows and velocity is important. Multi-phase systems, porous materials, and of course partly because of that most of these are going to be optically opaque as well. So we need a non-invasive tool, so that's why many of those things we're interested in human bodies as well. But it's why MRI is such a valuable non-invasive tool. I've just got a couple of examples. This is a fluidized bed which would be used for catalytic cracking of oils. This is an example of drug dissolution in a USP4 cell, looking at the time evolution of the structure of the tablet. So I've just got one slide here which is on how we get an MRI image. I'm sure some people will be very familiar with this. But I've put it up here because we've got to think about the type of data that we acquire and how we might be able to speed up the acquisition of that. So the basics of magnetic resonance generally, nuclear magnetic resonance, is that the nuclear spin is oscillating, or the signal is oscillating with a frequency omega here, which is proportional to the field strength observed by the nucleus. And so the way that we access spatial information, so the imaging part of NMR, is by applying a constant gradient in the magnetic field across our sample. So now if we've got a variation in the field strength across our sample, so we've got a variation in the frequency, and so we've got a relationship between the frequency that we're measuring and the spatial location of the material in there. And ignoring various other terms, we can say that the frequency as a function of position is proportional to the gradient strength G times the position vector R. And so looking at the signal that we acquire with magnetic resonance, or with MRI in particular, and so we've got an oscillating system, so we've got an e to the I theta type term in there. By substituting in this k vector, which is a constant, times g times t, it's actually just a time integration of the waveform, the gradient waveform that we're applying. This is a vector. By substituting this in here, we can identify that the signal that we measure as a function of k is given by this integration over our sample volume, where rho of r, rho is the spin density or the local concentration as a function of r, our position vector. So anybody's, if you're used to Fourier transform, you see that looks like Fourier transform. We have a Fourier transform pair here. And so what this is saying is that if we take our signal acquired as a function of k, remember this is, we can apply a different gradient as a function of time, it's an experimentally controllable parameter. If we acquire s as a function of k and do the Fourier transform, then we extract rho as a function of r. So rho, that's the spin density, the concentration as a function of position. So that is what is more normally thought of as an image. It's just intensity as a function of position. So what that says is that all we need to do is sample s as a function of k, do the Fourier transform, and that extracts our image. So what we'll be thinking about is this type of two-dimensional k-space raster. It could be three-dimensional for a 3D image in reciprocal space. If we acquire our signal as a function of these different values of k, where k is just the time integral of the gradient waveform, we can design sequences to acquire those data points in different ways. This is on a nice rectilinear grid that I've shown here. We just do a Fourier transform and that extracts the image. Or in our case, more likely to be something like that, which is a porous material there. We've got glass beads which aren't giving us any signal, and we're filling the void space here with liquid water, and we're getting the signal from that. So another thing that's been mentioned already today is that one of the reasons that MRI is such a powerful tool is because there are lots of different contrast parameters. So it's not, well, you can get information about where molecules are and how much is there, but also about their local molecular environment and so on. One contrast parameter that I'm going to focus on today is the ability to measure the speed of the molecules. And so we can actually do velocity imaging with MRI. I'm doing here just velocity of imaging of flow in a pipe at low Reynolds number, low velocities, viscous dominated flow. So we're looking at just a pipe flow here, flow going through it. This is sort of a cross section there. We're taking an image in the XY plane. And in this image, instead of the intensity showing how much liquid is at a particular position, the intensity here actually is directly proportional to the local velocity of the liquid. Now, for laminar flow, for low Reynolds number flow, there's an analytical solution to that. It should be a parabola, get quasi flow. And if we take a line out of there, I've plotted the data points and put the analytical form on there as well. And you can see that it is a highly quantitative technique. What we wanted to do, of course, is this is steady state. We'd like to be able to look at systems which are varying in time, look at high-speed imaging, and one of those things would be to go to higher Reynolds numbers. This is where inertial forces begin to dominate and you get chaotic time-varying flow in there. Just a quick slide on the sort of range of applicability. When you're designing the MRI, there are lots of different parameters to play with, and you can actually measure a very large range. You've got a very large dynamic range if you choose your parameters correctly. So this is just to show for example, you can typically measure velocities over around about 8 orders of magnitude at a push. So you can see, so velocity images you can get down to around about a micron per second, up to about 100 meters per second, using very different sequences and with different constraints. This is just some work we did actually with Ray Goldstein here in DAMT, looking at the velocity inside a single cell, where we've got velocities down of order of a few tens of microns per second, with a comparison with some modelling. This isn't our work, this is some work done by a group in Canada, but they're looking at velocities up to of the order of 100 meters per second. Right, but we're particularly interested in looking at dynamic processes. Many systems of practical interest are changing over time, as I've said before, either just changing velocity or often with structural changes as well. So there are different approaches that we can have to this. One might be just to, if we've got something that's changing, we can just do a time average measurement instead. So we'll say that our imaging information, our imaging time will be done over a timescale which is long compared to any temporal fluctuations we've got in our system. And certainly this can be very valid, can provide useful information. You're obviously losing some information about the short timescale fluctuations. And also it's only valid if your fluctuations are around an average value. If you've got any systematic changes, that's not going to be so good. But what we're mainly interested in is the idea of snapshot imaging. So that's acquiring all of your information, all of your image information on a timescale small to any temporal fluctuations that you've got in your system. And so typically that means speeding up acquisitions. Of course, depending on the system you're looking at, that might mean going from hours to tens of minutes, or tens of minutes to minutes. In here, I'm going to be thinking about systems changing over the timescale of tens to hundreds of milliseconds, so we want to get imaging times down to that sort of timescale. I'm not talking at all about periodic systems, things like the heart triggering that you can do, or pulsatile flow that you can trigger on, or stirred systems and so on. So can we use MRI to look at turbulent flows in particular? Well, this is something we did a few years ago, where we managed to acquire, so the idea of this is we've got our case-based raster, we need to acquire all of those points, and if you do it from a single shot, single excitation, we can cover this whilst getting velocity information as well as the information about where the particles are. We can get our velocity image here in 20 milliseconds. That would give us one component of velocity. If we want to get a description of the of 3 components of the velocity, 3 orthogonal components, then we can do that in 60 milliseconds. So let's look at that for pipe flow. And we've got increasing Reynolds numbers through here. At low Reynolds numbers, so I should say the color scale here corresponds to the velocity component in the direction of superficial flow. The in-plane component is shown by the arrows. We can see at low Reynolds numbers we get this same parabolic flow, it's steady state, but as you increase the Reynolds number you just lose a bit of symmetry here, and then we move to past the transition into turbulence to identify the vortices in there and so on. So we can actually we can show that the time scale of the imaging, 60 milliseconds here, is still short enough for this experimental system to be able to capture the velocities on a timescale short compared to those fluctuations, because we can actually monitor the timescale of those fluctuations as well. But of course, once you start going down here, you say, well, can we go further? There's still many systems for which 60 milliseconds is too long. So what we wanted to look at was other ways in which we might be able to acquire the information in a more efficient manner, in a more robust way. So particularly to get faster images, more robust way than what I've shown before. As the velocities increase, you start to get some errors due to higher velocities, and so we want to minimize those. And another thing that I didn't mention is, in the previous method that we were looking at, you acquired a velocity image, and then you have to wait typically a second or so, a t1 time, before you can acquire the next velocity image. So that means you don't get a time evolution. It would be nice to get that in as well. And then, as I mentioned earlier as well, the other question is, do we need to acquire all the data points? Can we think about something like compressed sensing for the for sparse acquisition and compressed sensing for the reconstruction? And can we think about systems, ways to acquire the data, the case-based data, which enable fast, efficient coverage of case space, but also some sparsity in the acquisition as well? So this is where we're looking at different methods of, say, what we have been doing previously is something which is at least acquiring information on this rectilinear grid. It's very nice in terms of reconstruction because you can just, with fairly little modification, just do a Fourier transform to your data if it's all on a regular grid. But it's probably not the most efficient way, so particularly in terms of hardware limitations, it's actually, usually anyway, it's the rate of change of the gradient, rate of change of the gradient strength that is a limiting factor. And it turns out that looking instead at a spiral imaging type methodology allows us to cover the same range of case space, the same increment in case space over in a more efficient way with a shorter time scale. So there are a couple of other advantages here. This is the pulse sequence, which I'm not going to talk about at all, but it's a little bit simpler than the previous one. It still requires fairly careful implementation. I say faster coverage of case space for given hardware limitations, so we're sort of cutting down about by a factor of 2 on the speed of this. Because of the order in which we acquire these data points either side of case space, it's also very robust, in fact, to high velocity effects as well. So we don't have some of the problems that we were seeing earlier. We've done this up to a couple of meters per second without significant velocity effects here. And the other advantage is that this is very suitable to a short recycle time. So we can look at the evolution of the system with a movie type acquisition without having to have a long delay time between one image and the next. And then, of course, as I mentioned, there's the idea of compressed sensing. So this is actually something we started with Andrew Blake, who at the time was across at Microsoft Research in Cambridge, back a few years ago now. And I think it's something that's become much more widely used over time. But the idea of other ways in which we can still reconstruct the information that we want, but from fewer data points, instead of using a Fourier transform, using some other optimization. And so actually, again, the spiral here is quite well suited to that. So this is the type of trajectory that we're now using, but instead of just using an Archimedean spiral, we've got a variable density. We can actually decrease the data points that are required as a function of position as we're moving further out in case space, and so reduce the number of points fairly easily by a factor of 4 in what I'm going to show, and still reconstruct quantifiable data of good quality. So here's the example of that again for flow in a, hopefully, for flow in a pipe. So the intensity here, this is just a single component of the velocity, but we've got the intensity, which is the velocity in the direction of flow of the pipe. So in this case here, we've got an XY slice. In this case, it's a vertical slice. But we're now acquiring this at just a bit over 5 milliseconds per image, so a frame rate of nearly 200 frames per second. So these have been slowed down by a factor of 10 compared to the acquisition rate, which for a technique which is typically seen as slow is a fairly good speed. To the extent that we're actually getting to the stage where we can look at gas-liquid systems, this is a gas bubble, air bubble in water, and we can actually track the bubble as it moves up through our system, identifying what's going on in the wake. Now, if we want to identify more carefully what's going on in the wake, we actually have to think about suspending this bubble. So we've got fluid passing down here, and we've got the bubble being suspended, and then we can just concentrate on take images on a plane below this and identify, well, there are several things we can identify from this. We've got the main counter-rotating vortices, but we can also look at the shedding of the wake. And actually what you notice, although you've got your predominant vortices here, there's a secondary mode as well, which is in plane, and that keeps switching around. And if we plot that at the same time as the direction of the wake, we can actually see that the direction of the bubble motion, then the direction of the wake and the bubble motion are in antiphase, as you can see along here. And this is something that has been postulated in some theory of bubbles and why bubbles wobble, but had never seen any experimental evidence for before. I don't think I'll go into the details of this, but what we wanted to do as well was look at liquid-liquid systems. It turns out that because of the chemical shift artifacts, you get signal from both different phases if we've got oil and water in there, and that complicates the system because we were relating the frequency to position, but now we've got a frequency component there because of the different chemical shift as well. But by designing a slightly different perturbed raster, we can then extract some information about time evolution, separate out essentially the chemical shift artifact from the chemical shift phase evolution compared to the positional component in there. And so this is an example for a oil droplet in water, and we can separate them out in terms of the intensity, but we can also independently get the velocity in the two different phases. We need to build in a model. We need to know about the difference in chemical shift separation for that. So I just want to finish off by thinking a little bit further about whether we need to take an image. So what we've been looking at before is a conventional imaging, maybe acquiring all of our data, our case-based data, and doing a Fourier transform, and then that extracts the image. Or if we're thinking about sparse sampling and compressed sensing, we acquire fewer data points, and instead of doing a Fourier transform, we do some other type of data reconstruction. But often what we're doing then is, instead of just using an image, I mean, images are nice and they can be pretty and so on, but we usually want to extract quantitative information from them. So what you're typically doing is taking that image, and then if this was an image of some bubbles, for example, we might be identifying the different bubbles in there, identifying their sizes, and building up a size distribution, probability distribution of bubble sizes. And if that's actually the information that we want, then there is a question as to whether we need to go through the complex image acquisition and reconstruction when maybe we could actually get straight to this information by acquiring far fewer data points and building up a model for how the experimental data may vary as the state of depending on the state of the system, and then using Bayes' theorem to extract out just the information that we're after. So going back to gas-liquid flows, but in this case, instead of a single bubble, we've got lots of bubbles within the system. Very difficult generally to measure with different measurement techniques because they're optically opaque if you've got many bubbles in. They're highly dynamic, and as soon as you put any probe in there, you change the system. So you can try to do this by imaging, and you can in fact get somewhere by acquiring that information case-based very quickly and doing the Fourier transform. But what we're going to think about instead is how the data that we acquire in case-base is going to be affected by the bubble size. So if we take just this would be a real projection of a bubble of a certain size, say 4 millimeter bubble. We of course acquire in the Fourier transform of real space. So this is what our acquired data in one-dimensional case-space would look like. And if we think about a different size bubble, a broader bubble, then that's going to have a very different characteristic in our experimental data acquisition domain. And so by building up a model for how our acquired data will vary as a function of the parameter, the state of the system, the parameter that we want to measure, we can build up a model which enables us to extract out the bubble size distribution, in this case, just from acquiring a few data points in case-space, a few experimental data points. So this is an example of a very low gas volume fraction where we can actually do optical measurements on it as well, so we can do a comparison. These are both at about 2 volume%, but we've got a different distributor in there, so we've got smaller bubbles and large bubbles. And as I say, we can do optical measurements, and we can do this Bayesian analysis, and you can see we get good agreement between the two. As soon as you go to higher gas volume fractions, you can't do the optical technique anymore, but the Bayesian analysis of magnetic resonance, of course, works just as well. And just final example of this in action is this is looking at, again, a bubbly flow going up, and what we're going to do is change the bubble size by injecting a surfactant. You inject a surfactant, you reduce the surface tension, the bubbles will get smaller. And what we've got is, if you can just about see it, the slightly blue region here is where we're injecting a surfactant. Another thing to note is that bubbles which are smaller than about 1 millimeter diameter should be spherical. When they get larger than that, they become elliptical with a larger XY component than a Z vertical component. So at short times here, before we put the surfactant in, the radius is more than 0.5 millimeter, so they're elliptical, and we've got the X component much larger than the Y component, so that shows, the Z component shows that they're elliptical. We put in the surfactant, and immediately the bubble size drops to below 1 millimeter diameter, and it also collapses to the Z and the X. So we can immediately see that we're getting spherical bubbles, and then as we stop it, we see slowly the evolution as the surfactant gets entrained out of the system, and so it returns to these larger elliptical bubbles. And one of the things I wanted to highlight about this is, obviously this is a specific application, but it's also, compared to the other images that I've shown, are on relatively high spec equipment. They're sort of superconducting magnets, fast switching gradients and so on. This actually, just by thinking about a few data points that we might need to acquire, this is a very simple type of data acquisition. So potentially you can move from a much more complicated research grade type experiment to a permanent magnet system which doesn't require cryogens at all, something that can be benchtop, even potentially handheld. If you're looking at a very specific thing that you want to measure, it may be the size of something inside something, or whether you've got something that's turbulent or laminar flow within something which is optically opaque. So potentially you can, if you know what it is, it would only be for a specific application, but you can think about producing a much simpler system, acquiring just a few data points on a relatively cheap machine. So I think I should finish there. Hopefully I've shown that velocimetry, MRI velocimetry, can be used for a wide range of dynamic processes with the kind of speeds that we're getting up to. I think one of the things we started at, and an interesting development, will be thinking about more intelligent both data acquisition, what data points we want to acquire, and also reconstruction, if there are ways that we can introduce extra bits of information, whether it be what data points we then acquire later on, or different bits of information into the reconstruction, some of which we've seen today, to help reduce acquisition times further, or build up, get greater information, greater spatial information within the system. And also, following on that theme, can we actually acquire fewer points but not worry about an image, and think about other types of data analysis, again, probably with some prior knowledge of what system it is that we're looking at. Thank you.
Are there any questions?
How do you choose where to place your data points in K-space?
Well, so you're limited to a large extent by how fast you want to go. Let's say the slew rates of the gradients. We've used a variety. Essentially, we're weighting it towards the centre, and we've got a distribution where it's a variable density, where the density is decreasing as a function of distance from the centre of K-space. It's not a linear function. I can't remember exactly what it's. Something like 1 over r squared, or something like that. I can't remember exactly what we used here. We've tried a variety of different things in terms of how sparsely you need to acquire those data points. But you are also limited by the slew rate of the gradient to some extent.
Because if you're interested in the size of the bubbles, then it's probably like the edge information that's important to you, not so much the low frequency information.
Yes. Well, so the information that I was showing for the bubbles there was specifically for the Bayesian analysis. So there you are looking at a specific range of K-space, and it would not be the stuff very close to the centre in particular. For the velocity imaging and for the imaging of the velocities in the wake, that's obviously not so much the case. Thinking about the transform that you use as well, will depend on the type of thing that you're looking at.
Just to follow that up, do you vary the sampling as a function of time, or is it fixed over time? The case-based one.
So for a single two-dimensional image, we are varying it from the center of case, so we're doing a center out spiral, and we're varying it from the center of case base out. So but then when we do our second image, we would then repeat that. We have actually also been looking at, so what we'd like to do is acquire this sort of information in 3 dimensions, so then you get a full description of the flow. And there, obviously there's more data that you need, but you can, what I haven't been showing here, but we've been looking at, is using the time as a 4th dimension, so you've obviously got sparsity in time as well. And so then with a very sparse acquisition, but with enough sparsity in time, you can actually do 3-dimensional images on a time scale which is not much longer than what we've got here, but say 3 space dimensions, but with 4D reconstruction on that. Yeah.
But what people do is fill in as you go over time.
Yeah, exactly. So each different.
People report 20 or more fold acceleration.
Yes. So I think we did 4% sampling. Yeah. So that would be 20. Yeah. Exactly. With each different spiral in time, or we had a fixed number of spirals, 3-dimensional spirals that we were using, but changing the orientation of that between each.
Andy, what's the state of the art in region of interest selection? I mean at the actual acquisition stage, because one of the things that coming to this meeting and sort of thinking about is that the kind of case-based only approach might be quite powerful, provided you've already identified the region of real space where that information is important. I mean, are there region of interest selection techniques that would be compatible with a case-based only acquisition?
I think there certainly would be. It's not something we've done. Well, we've not applied significantly to this. We've certainly done some region of interest things. Another area, without thinking about the selective excitation, might be surface coils as well. So this clearly with particularly medical systems rather than ours, you can have sort of 256 separate channels on them, and so you have lots of different. You're recording data which itself has lots of spatial, locally spatialized, locally selective information already encoded in it, without actually worrying about those sort of selective excitations. You could do something. The more pulses you get in there, you're probably losing your movie type acquisition, but there might be ways around that. Yeah. Interesting ideas.
So thanks, Andy, and can we, or John?
I was just wondering, in your Bayesian analysis, what kind of parameterizations are you using for the model? I mean, are you putting priors on things like the number of bubbles, the size of the bubbles, or are you?
No, it's very non-specific prior here. So for this example, we were just basically putting limits on the size. The size could not be larger than half the diameter or the radius of the system, or something like that. So it was only just Bayesian, should we say?
Okay.
But it's a probabilistic analysis with some fairly non-specific.
And in your posteriors that come out, what kind of information do you just extract the bubble size, or can you extract other information from?
So we were extracting other information. We were extracting information about the distribution of bubble size, along with the voidage as well,
okay.
Which is another important parameter. And so you need to make certain assumptions about the distribution shape. But again, you can actually you can do tests for those. You can put in a variety of different shapes and extract parameters. So typically standard deviations and whether it's a Weibull shape or a Gaussian shape or something.
And let's thank Andy again for the talk.